Okay, we're doing two warm-ups in preparation for tomorrow night's quiz on Chapter 9. We did a couple last night, several of you during office hour time have asked some really good questions about Chapter 9, but I want to make sure we cover these also. So this first one, it's got these weird exponents, and the way we attack them is we did a substitution. We made up some variable, and for some reason, we always use the letter U, although you can use any other letter you want, okay? And we let it equal the lowest power, x to the 1/3. Now, that implies that U squared will be x to the 2/3, but that confused people. So I suggested that you just kind of don't worry about it. If you had U equals x to the 1/3, if you square both sides, then you'll get that statement. Okay, but don't worry about it. Then this problem now becomes 2u squared minus 5u equals 12. But we know that because it's a power equation, it must equal 0. 2u squared minus 5u minus 12 equals 0. Okay. It's quadratic, it's power of 2. It will somehow factor. Okay. I'm pretty sure that's correct if I use my AC and all that other nonsense. Also, remember, one of the things I told you guys was something called the belly button. You can real quick check. That makes positive 3u. That makes negative 8u. Does negative 8 and positive 3 add up to negative 5? Because I said the innies and the outies, that's your belly button, is in the middle. That's how that belly button rule works. So it's a real quick way to mentally check your work. So anyway, where's the glitter? Okay, good. So skipping a step, this becomes u equals negative 3/2, or u equals 4. Is that okay with everybody to skip that step? What I did is took this equal to 0 and solved it in my head and got that. Set this equal to 0 and solved it and got that. But now here comes the tricky part. Okay, this is the value for u, but I was solving an equation that was using x as its variable. So I have to go back to my original variable, and I have to go back to this substitution. U equals x to the 1/3. So this allows me to write x to the 1/3 equals negative 3/2. Instead of u equals negative 3/2, I have x to the 1/3 equals negative 3/2, or x to the 1/3 equals 4. Okay, so that's the you have to go back and eventually unsubstitute. You have to go back to your original variable, whatever that was, and that's what this tells you. This helps you remember that. Okay, now we had all kinds of issues. What do you do now? How do I solve that problem? Okay, some of you liked to remember that the 1/3 power is the same as the cube root. X to the 1/3 power is the same as the cube root of x equals negative 3/2. So to get rid of a cube root, you would cube power it. The cube root, the cube power cancel out. We're going to get x equals whatever that is, negative 27 over 8. Negative 3 cubed, 2 cubed. Others of you have said that you would prefer to raise it to the 3rd power right away. because you know that a power raised to a power, you multiply them, and x to the 1/3 times 3 is x to the first. That equals 64. So that means x equals 64. And so now you put them into one big solution set of -27/8 and 64, and you're done, living happily ever after. Okay. Guaranteed tomorrow night, guaranteed when we get to the chapter 9 test, guaranteed this kind of problem with a substitution tomorrow night and on the chapter 9 part of the test, exam, whatever it is, 3 or something. So any questions? I'm going to have to erase this side of the board in a minute over here. But are there any questions about my work? I'll put the solution over here again. No, you guys are all happy. You can all do this then tomorrow night. You can do this on the chapter 9 test. Okay. Can I erase? I need to point out something. I've done this 2 different ways, only to show you 2 different ways. You don't have to use this. If you like, change it to the cube root and then cubing both sides this way, great. Do it that way. If you like this technique, great. Do it that technique. You don't have to do it 2 different ways. I show you the 2 ways. You pick the way that's best for you. All right. I'm going to erase. Has anybody got a screen? No. Okay.
I had a kind of unrelated question for you.
Okay.
So, I know you said that there's no tutor embedded into 104 for the summer.
Right.
Is tutoring available at all through the college?
Anne, are you here?
And
Anne?
she was going to be gone today. I did a tutor with her today.
Oh, okay. I don't know. I will look that up. So summer tutoring.
Because I know they have tutors available, just like at random, but I don't
Right.
know if they're available
At
during the
this,
summer.
yeah, I don't know. That's a good question. I'll see if I can find that out. That's a very good question.
Thank you.
Yeah, what about NetTutor? I'm wondering.
Well,
if that's
NetTutor should be
available.
available all the time.
They're always awesome too on other courses.
Are they really?
Oh yeah, English and history.
What
Really
about,
good.
do you know anything about, I've only heard stories about it and I haven't heard anything bad about it. You know,
I
so
don't know anything about math, how that would work, but I know with my essays, they proofread, they give you ideas and ways to
Really?
change it. You just tell them what the goal was and they'll pretty much grade it like a teacher for you or professor, and then tell you how to correct it. But yeah, I don't know how they do it for math, but I
Are you
guess.
talking about the English, what is it called, through SDCCD?
Well, no, on your Canvas, there's a link. I think you've actually posted, my professor, a link to
Yeah.
NetTutor. It's in the
it's on the
module.
left-hand, it's on the
Yeah.
left-hand column of any Canvas you log into.
We have access to that for
Free,
free.
and it tells you, and you
Yes.
pick through the subjects and tell it what you want. And those people are there. Yeah, they're pretty
You
cool.
know,
Very
that's
cool.
what you do. That's one thing you could do. I'll find out if Mesa has anything, but you can get on the NetTutor tonight or tomorrow or something like that and say, what about the summertime? And see if whoever you talk to can give you some guidance on the summer also.
Okay, yeah, for sure. I'll do that.
Let us know, because that would help everybody then. That's cool. Thank you, both of you.
Yeah. Thanks.
Okay,
And it's a good idea for me too. I think I might take us up on that.
okay. Well, it would be good to hear. I mean, if you guys are getting tutoring from NetTutor, that's awesome. I mean, that is really good. So, and it'd be good to find out if it's good. I mean, sometimes people could do well in English, and then when it comes to doing math and science, they just kind of go, I can't tutor you, you know. But I do know they told us when we bought that program, Net Tutoring, or bought into that, that they had dedicated tutors, people that were supposed to be knowledgeable in those areas. So Let's hope. Okay, back to this one. Now, there's two ways we can do this problem. Okay, the hard way, don't copy this down yet. The hard way would be to FOIL this out. Don't copy this down. And then distribute. And then make it equal 0. And then hope and pray that you haven't made a mistake and factor it. That would be the hard way. Okay, you guys follow what I did there? I hope you didn't copy it down. You square it out, then you multiply through by the -2, then you combine like terms and make it equal 0. And then you start the algebra. You start using either the quad formula or factoring or whatever. That would have been the hard way. One of the things we started chapter 9 with was something called the square root property. Okay, so I'm going to show you. And that was, in this case, you could take 5 away from both sides. So you have -2 times 3x plus 1 quantity squared equals -16. You can divide both sides by -2. And you get this quantity by itself. Okay, now the cool thing about this quantity and this particular problem is that all of your x's are inside the quantity squared. And that's a very special case. All of your x's are inside the quantity squared. So the process we learned was you could square root both sides. That will cancel the square power, but you have to introduce a plus or minus. That was the trade-off. This method is much faster, okay, but you have to remember to introduce a plus or minus. So next, where am I? I got room. Okay, I'm going to do two things at once now. I'm going to subtract 1 over here, because remember, our goal is to get x alone. So eventually I've got to get rid of the 1 and I've got to get rid of the 3. Okay, so I'm going to get rid of the 1. And at the same time, so I have 3x equals -1 plus or minus. I'm going to simplify my radical. We always simplify radicals to radical 2. And then to get x alone, I divide. So x is -1 plus or minus 2 radical 2, all divided by 3. Okay, yeah, I'm still on the screen. So if you had done this problem like I showed and then erased, if you'd FOILed this out, squared this out, and then used the quad formula and all that crud, this would have been the answer. Okay, but because all of the x's were inside the quantity squared, that's a very important condition. All of your x's were being squared somehow. We could use this one shortcut. The question is, do you have to do that? Absolutely not. Okay, if you think you've got too much to remember and just want to go back to either factor or quad formula, that's strictly up to you. Okay, but my job is to show you quicker ways, more efficient ways to work through the problem. And that's what I wanted to show you there. Is that okay with everybody? Now, whether or not there's a problem like that on the test, I don't know. I think there's one, maybe. I think. All right. I'd like to erase the board and go on to new stuff. Did I start the, please God, tell me I started.
Yes, you're recording.
I'm recording. Okay, thank you. It usually tells me somewhere that I am, but I don't see it on my screen. Oh, well.
Upper
right.
left corner on our
No.
screen.
On your screen? Yeah, my screen just says switch cameras. I don't see it. Oh, well. All right. So are we okay with those two as review questions?
Yes.
Okay. Then let's go back to chapter 10, which we started last night. Okay. In chapter 10, as a quickie review, we started with functions, and I'm not going to review them right now. Okay, but I will tell you we started with what was called composition. And that's where we use that silly little circle. And we had things like G composed with F and all that kind of crud. Okay. Okay. And we also started talking about something called the inverse, which is where we use notation like F to the -1 of X. But it's when you put a -1 power on a function. Choice of words here is important. When you use the -1 power on a function, you say F inverse of X or the inverse of F of X or something like that. It is not the same -1 power that we're used to flipping. So that was the concept of functions. And we did quite a bit of that. I kind of probably burned you out. The next thing we got into, oh, we did more. Well, nah, I'll just leave it there. We did because we did a lot more. Then we got into right at the tail end of class, an exponential graph. Right at the tail end of class, we did that. And so we started graphing y equals 2 to the x. Okay. And the best way to do it, at least until you're comfortable with it, was to build an XY table with 0, 1, 2, and then -1, -2, -3. And that introduced, actually, when we do, if we did y equals 2 to the x minus 3, what that introduced for us was a whole new concept of, wouldn't it be nice if somebody would introduce a whole new concept of an ink pen that lasted more than one evening? Of course, I shouldn't complain. My grandson was over here and he says, I want to write on the board. So he probably used up half my ink anyways, writing on the board with all the pretty colors. Okay. And this introduced the concept when x is 0, y is -1. So this introduced the concept of a graph that looks something like this. So if you built an XY table for this and didn't screw up your arithmetic, you got something that looked like this. And we introduced a line down there that was called an asymptote, ASYMPTOTE, asymptote. And it's this invisible line that the graph will come closer and closer and closer to, but never touch, at least mathematically. Okay, I got a fat pin here, so yeah, eventually the pin will cross the dotted line. Okay, but right now it won't. Okay, so we have an asymptote, and part of your work, I'm going to ask you to always label the y-intercept, which means this is 0, whoops, should be -2. Should be down here, -2, sorry. Now, how did I get that? The exit or the y-intercept means x is 0. So 2 to the 0 power is 1. Take away 3 is -2. When x was 0, y was -2. Okay. And then building my table, I get this shape and we're all happy. But the asymptote is also y equals -3. That's the asymptote. I should put it probably out here. Okay, that's an important feature of this graph. And the instructions, when I ask you to graph this on exam number 3, one similar to this, will say graph this, label the y-intercept and the asymptote. This line, whatever that is. Okay.
Wait, so asymptote is 3 equals -3, but the equation up top, it uses the same variable?
It turns out when you start plugging in numbers, when you start plugging in numbers to here, when you go your x, y, okay, and when x is 0, y is -2, when x is 1, y is -1, when x is 2, y is 1, good enough. So that's how we get these points. But when you start putting in negative numbers, remember we did this and people were using decimals. When you put in -1, you get 1/2 minus 3. Remember, a negative power just flips it over. So 1/2 minus 3 is -2.5. And you put in -2, you get 1/4 minus 3, -2 for x, so that's 1/4, flip it, minus 3 is -2 3/4. And we discussed yesterday what's going to happen as x gets more and more negative. So as x goes towards -infinity, so as x gets more and more negative, what's happening to these answers here? Well, they're changing, but they're getting more and more to -3. And so we say they approach -3. Okay, which just happens to be that number out there.
So that the y equals -3 it's saying that y can't equal -3?
Oh, it's just the line. It's the horizontal line, y equals -3. And because we put it as a dotted line, we will assume that that means it's the asymptote. Yeah, it's the line that it's the invisible line that the graph can't touch.
Okay, and that's just how that's
Yeah.
written. Okay,
Yeah, that's just how you want to give the viewer, in this case me, the instructor, some sense of what's this graph doing. Is it going here and then suddenly shooting down? Or what's it doing? What's its behavior? How is it acting? So you're saying, no, it's going to come out here and it's never going to quite touch that line, y equals -3. And that's just giving me a clue that you know what's happening. Okay or not okay?
So
okay,
just
okay,
Just
sorry.
for this problem, I was just kind of playing around with Desmos and putting in different numbers and seeing what happened with the curve.
Yeah.
So the first number raised to the x power is always going to be the number that it can't touch. And then the second number will also be the y that is never touched, right?
Wait, I didn't understand. This is the number that y will never touch. I'm not sure I understand what you're talking about there.
So that's the asymptote. So that, or no, never mind.
That's the
No,
asymptote.
that's the asymptote. Yeah, yeah. And then 2 is the one that it'll never.
Two is just your base. Okay, let me go back and give you a little bit of theory, math theory on this for a second. Okay, and because I'm really glad to hear that you're messing around on Desmos. That's good. That's great.
I was trying to find a pattern in the numbers to see if I could figure it out in my head.
There is a pattern, and I'll show it to you. Okay, in this is graphing theory, graph theory, and As we move higher and higher into math, we end up studying more and more graph theory, because you know what? The honest God truth is we don't want to take the time to build a table of values. We really don't. So instead, we look for something called a parent graph. The parent. That's the main graph. For example, y equals 2 to the x. So if we build a table of values for that, it will look like this. And it will guaranteed never touch the line where y equals 0. Now that's called the parent graph. So what do we do with it? Well, we do things like, oh, gee, what happens when we have y equals 2 to the x, the parent, plus 1? Well, what does that plus 1 do to the parent? It literally lifts the graph up. Okay, so this one would be, okay, everything is plus 1. It literally lifts this up. This is 0, 2, and this asymptote is y equals 1. Everything got lifted up by 1. That's what the plus 1 is. That's called, okay, it's known as a vertical shift. It raised the graph up vertically 1. So in higher levels of math, we tend to memorize the shape of the parent graph. Okay, that I can remember. But then we go, what's that do? Well, it just takes the parent and lifts it up 1. That's all. Well, what if I gave you this? Y equals 2 to the x minus 7.
Bring it down to -7.
Going to drop everything. It's going to take the parent graph, drop it all down 7 units. Okay.
What if you did 3x to the -7th?
3 to the x. I'll get there in a second. I'll show you. That's a very good question. Okay. So my asymptote is going to be down at -7. Okay. So y equals -7. My intercept on the parent graph was 0, 1, but if we drop it down 7, it'll be 0, -6. And roughly that's the shape of the graph. Okay, graph theory. Okay, Mitch was asking the question, but I'm actually talking to everybody. So questions about if this is the parent graph, okay, do you understand what's called vertical shifts? Vertical up, vertical down. The plus 1, the -7 just moves the graph up and down. Is that okay with almost everybody?
Yes.
Okay, now, Mitch, I'm not answering your question yet, but for everybody, we're in chapter 11, which we're not at, so relax. We're going to study y equals x to the 2, different graph. Different graph. This is 2 to the x. In chapter 11, we're going to study x to the 2. And for what it's worth, it's called a parabola, and it looks like a U. Okay, that would be called the parent graph. If we have y equals x to the 2nd power, that's the parent graph. So everybody should be able to sketch, what about y equals x squared minus 2? What would happen?
Probably bring it down to.
Bring it down to. The same theory has to always work. Okay, so yeah, if -2 brought this exponential down, then -2 must bring this parabola down. So it would look something like this. The whole graph shifted down 2. Okay, graph theory. Does that kind of okay. I'm not going to go off the deep end in graph theory. I can, but I'm not going to go off the deep end in graph theory too much. For this class, your safest thing, if you're not sure about graphing, is just build that table of values. Now, I'm not done talking about graphing, but I kind of wanted to give you that theory. Okay, Mitch then asks another question. Okay, so don't blame me, blame Mitch.
I'm okay with that.
Oh, we are.
Oh, yeah, okay. Okay,
Again,
yeah, we'll get you.
chat.
I know where you live. Okay, okay. So what if we gave you this one? What if I gave you this equation, y equals, I'm going to be a little bit, you said 3, I'm going to use 5 because I want a bigger, I want it to stand out more. What if I asked you to graph y equals 5 to the x? Okay, so let's look at this. Let's build a table of values real quick. If x is 0, y is 1. If x is 1, y is 5. If x is 2, y is 25. Holy crap. I don't need to go any higher than that.
The intercept would be 2.
Okay. If x is -1, y is 1/5. If x is -2, y is, whoops, 1/25. If x is -3, y is 1/125, because you're just taking 5 to those powers. Now, don't copy this next graph down yet. Don't copy it down yet, please. If I just graph these, 0, 1, 1, 5, 2, 25, way the hell up here. Okay, -1, 1/5, -2, sort of, -3, sort of. Okay. If you just graphed this on its own grid, okay, you could look at this and you could look at this and you could say they're the same. Okay, and I would say, well, they're the same shape, but they're not the same. All exponential curves will have the same shape.
So it makes it
Okay, for some reason, my high school students like to call this a J curve. And honest to God, I guess I could see a J in there, sort of, but I don't see it. So separately, you can't really tell how different they are. But if we put them on the same grid, if I take these numbers and put them over here, when x is 0, y is 1. When x was 1, y is 5. When x is 2, y is 25. When x is -1, y is 1/5. Look at what this graph looks like here. So by putting this graph on the same scale or grid as this graph, you can now see the difference. Okay. What happens to the 5? Well, it makes the graph get taller faster. Okay. Some people say it makes it skinnier also. Okay. But the base 5 makes it go higher, faster than a base of 2. Okay. And if you play with that on Desmos, if you go into Desmos and graph a whole bunch of them on desmos.com,
Yeah, I was doing that while you were teaching here.
and you graph, oh, good, so you're not listening to me, thanks.
I can
Y
multitask.
equals 2 to the x, y equals 3 to the x, y equals 5 to the x, and you look at each one of those, okay, you'll see how they all have roughly the same shape, but some are steeper than others. Okay, if think about, just take a guess, what about y equals 10 to the x power? Okay, that's going to be that's going to be so incredibly steep, I can't even draw it. Y equals 10 to the x power would be like right in here somewhere. I don't
Yeah,
know if
it's
you
more
guys
of a
can
cliff at that point.
it's more of a what?
A cliff, like a sheer
Yeah,
cliff.
yeah. But I don't know if you guys can see the blue or not here, but Desmos.com is a great place to play with some of these numbers and see what happens when we change the base. Remember, in exponentials, 5 is called the base, x is called either the power or the exponent. If you change the power, the base rather, what happens to the shape of the curve? Okay, and that's all a whole bunch of graph theory. And mom does ask a bunch of questions about that. Okay, I will not ask those questions. Not on the exam, maybe on the quiz, okay, but definitely not on the exam. Okay, I will only ask you to graph this, show me the asymptotes and the domain and the range. Okay, I want to leave you with one more thing here. Mitch, I'm not sure I've answered your question. Have I or not?
No, you did. And yeah, more than, yeah.
Yeah, okay. That's when you get me, you get stuck. I always talk too much. I
No,
give
it's
you
okay.
more than you wanted. Okay, much more. Can't you guys tell by all the emails I send out? I'm really into giving information more than you wanted, more than you needed, more than you cared about.
You're not my worst professor at that.
Oh, really? Oh, that makes me feel so good, the way you said that.
I know, I was gonna say.
You're not the worst.
That's a
You're
nice
the
square.
I
second to
think
the
it's
worst.
nice.
Thank you.
I appreciate it because I totally forgot about summer registration. So
Oh, well, there you go. It's like my grandkids. They've adopted something. My name is Pop Pop. Okay, that's the name they call me by. Pop Pop. And it comes because that's how I made my granddaughter laugh and giggle, because I could go like that, and she just thought that was the greatest thing in the world. Okay, so now I'm Pop Pop. But if I do something wrong or silly or something, they just get this really offended look and tone. It's like, oh, Pop Pop. Already they know how to shame me. Okay. All right. Last thing I want to do on graphing.
someone just put in the chat pop squared and I'm dead.
Pop squared. Okay, Pop Pop. Yeah. I even have a hat that says that. So what about this? Y equals 2 to the negative x. Now, I don't want you to panic on this, okay? That's why I'm showing you this. You're going to run into this a little bit. There's 2 ways to attack this. The first way is just directly, okay? Just start building your table. Well, if x is 0, that's still 1. If x is 1, that's 2 to the negative 1, which is a half. If x is 2, that's 2 to the negative 2, which is a fourth. Okay, now hang on. What if x is negative 1? That's 2 to the negative 1. You guys see, if x is negative 1, then we have a double negative there. So that becomes 2. And what if x is -2. Well, that's 2 to the -2, which is 4. Okay, got enough. I know it's going to be some curvy that looks like this. So let's look at it and see what it looks like. When x is 0, y is 1. When x is 1, y is a half. When x is 2, y is a fourth. Uh-oh. When x is -1, y is 2. When x is -2, y is 4. So look what this graph does. Whoops, well, it's not supposed to do that. It's supposed to do that. So what did the negative power on the exponent do to this graph?
Inversed it.
Reversed it. Okay, where this graph, think about this. If you look at it, when x is negative, y is small, but as x gets positive, y gets bigger. So this goes from small to bigger as x goes from small to bigger. But think about this. As x gets bigger, y gets smaller. So it's the reverse. It reversed it some.
If you put -2 in there, then it should inverse it to the bottom side, correct? Point going down.
Yes.
I put -2 over -x.
Wait a minute.
All
What's
right,
your equation?
-2 to the power of -x. And then it should make it go the opposite direction, but downward.
Yes.
Let's say that.
Well, nah, you got a little hang up here. Whenever we do exponentials, okay, y equals something to the x power. Whatever this something is, it can't be negative, and no negative. Okay, so what you're doing is reading the question wrong. I understand what you said. Okay. You can't, not for graphing. You can't graph y equals a negative number. For example, if I said graph this, -2 to the x, you can't. Desmos won't do it even. Okay, it'll bounce around or it'll do something weird. But what you saw, Mitch, and this is really subtle, so I need you guys, we've done this in the past. Okay, y equals -2 to the x. That's what you said. Now, there are no parentheses there. So technically, this is y equals -1 times 2 to the x power. So we do the power first and then multiply it by -1. That's what's going to cause it to flip down. Okay, so notice I wrote this as a quantity. This is impossible. Go try that on Desmos. It won't like you at all. Okay, it really won't. It'll maybe bounce up and down or maybe give you an error, but it'll be something really weird. But if you write it this way, you have to remember that's -1 times 2 to the x power. We're going to come back. We're going off the deep end on this. We'll come back
Right. Yeah.
when everybody has had a chance. So anyway,
Professor, how do you enter the x power on Desmos?
how do you
No.
enter any power?
any
Y
power.
equals 2 up caret x.
Okay, thanks.
And it automatically then turns it into 2 to the x power.
Awesome.
And that, by the way, is how you enter simple powers on mom even. Mom will accept that 2 up caret x or whatever you want to do. Okay, mom will interpret that as power of x.
Perfect, it works, thank you.
Yep. Okay, anybody else? So chapter 10.1 was all about functions. Chapter 10.2, we have exponential graphs. And I would simply say build a table. For those of you who are fighting with all the theory and you're going, oh my God, too much crap to remember, just build a table of values. And the key then is get your arithmetic right, because that's what it comes down to. Now, what I want to show you still in section 10.2, still in section 10.2 is something called exponential equations and parentheses same base. Okay, and before Carmen asked me, next week we'll get to exponential equations with not the same base. Okay, they're much more difficult. This is easier, so we'll cover it now. So, example. Suppose we had 25 to the 3x minus 4 equals, I don't know, 5 to the 7x plus 2. And I wanted you to solve this. 25 to the 3x minus 4 equals 5 to the 7x plus 2. First off, this is an exponential equation. Duh, because it's got exponents in it. That makes sense. Okay. But the bases are different. But the question is, could you, with your vast knowledge of math and exponents, make the bases the same? Can you use your X-ray vision and look inside of 25 and see it as 5 squared to the 3x minus 4 equals 5 to the 7x plus 2? So by changing 25 into 5 squared, you're working towards same base. Now, hang on, we're not done. What do you do with a power raised to a power? What's the rule? A power raised to another power.
Multiply?
Yep. So this becomes 5 to the 6x minus 8, 2 times that, equals 5 to the 7x plus 2. So this is the game right here. You look at this, you say, with a little bit of trickery, I can force the bases to be the same, 5. I have to know my rules of exponents, okay, but the bases are the same. Now, if the bases are the same and these are equal, then what can we say about the powers? If the bases are equal and the whole sucker is equal, if this is the same and this is equal, then what's the only logical conclusion that we can reach?
Powers are equal.
Powers have to be equal. So you can just drop the base and work with only the powers. Okay, so take away 6x, I get x. Take away 2, I get negative 10. There's my answer. I just solved this problem. Okay, so that's an example of an exponential equation, an equation with exponents in it that happens to have the same base. Okay, we use our knowledge of exponents to get them to be the same base. Then we just ignore the base. We drop the base and work only with the powers. Okay, I've got more.
Are you gonna
Okay.
do one that's not so pretty?
Well, yeah, I'm going to show you the trick. There's two tricks that we have to worry about, but that's the basic idea right there. Make them have the same base somehow. All the problems in 10.2, the exponential equations, you will be able to make them have the same base. Okay. Later in this chapter, they won't be. Okay. Example of later, don't copy this down, but suppose you had 7 to the 4x plus 1 equals, I don't know, 15 to the 2x minus 3. There is no way in the world you can use your knowledge of exponents to turn the 7 or the 15 into something that are similar to each other. There's no way. So we have a whole nother way of solving this problem. Okay, much more complicated than this. So be happy for this. Okay, so Mitch wants one that's tricky and complicated.
I was just saying in the chat, mom's equations sometimes are extensively more difficult than what you've given us.
Yeah.
So
Okay, so what if I had 4 to the 3x plus 1 times 8 to the x minus 3, oops, equals 32. Oh, that's going to trick you. To the 5x, okay, minus 7. This is going to trick you. So I want to walk you through it. Okay. Do not, okay, first off, you can't multiply these together. You can't say 4 times 8 is 32. Okay, that violates everything about Aunt Sally. You can't do that. So can I reduce these all to a same base? Is 4 somebody to a power? Is 8 somebody to a power? Is 32 somebody to a power? You have any ideas?
can you use 2?
2. Okay, 2. And that's just going to come from your knowledge from working with this, but your knowledge of powers. So 4 is 2 squared to the 3x plus 1. 8 is 2 cubed to the x minus 3. And 32 is 2 to the 5th to the 5x minus 7. Okay. So that's the first thing. You've got to look inside all of the bases and ask, can I shrink them down to the same base number? And it's got to be to a power, 2 to a power, 2 to a power, 2 to a power. Excuse me. So if we do power to a power, this becomes 2 to the 6x plus 2. Power to a power, multiply. Times 2 to the 3x minus 9. Power to a power, multiply. Equals 2 to the 25x minus 35. Now I'm doing quite a bit in my head. Does anybody have
Yeah,
questions
that's
or
right.
what? But does anybody else want me to slow down? Do you have questions? Do you understand what I'm doing? Okay, I don't hear any yelling. Now, before, if you go look at the problem, I think I had the, I don't know, 5 to, I don't know what it was, 3x plus 2 equals 5, or maybe it was 6x plus 2 to 7x minus 3. Whatever that was earlier, it doesn't matter. The key there was I had 1/5 base on one side, 1/5 base on the other side. You can't see it because of damn glare. Okay, but the key was I had a single base on each side. What I'm trying to get at is that you have to combine these two. So let's go back to your rules for exponents. If you had 2 to the 3 times 2 to the 7,
You add them
what do
together,
you
right?
add them together? The rule was keep the base number 2, add the powers 3 plus 7. That was our basic rule of exponents. When I was multiplying with the same base, I keep the base, add the powers. That's what the rule was. So right here, it's the same rule. I'm multiplying, so I keep the base 2, and I add the powers, 9x minus 7. In adding the powers, I'm actually adding like terms, 6x and 3x, 2 and negative 9. So in your notes, maybe write a little aside off to the margin or something like that, that I used this basic rule for exponents that said when you're multiplying with the same base, you keep the base, you add the powers. And that's what I did here, except my powers were a little ugly. Okay. Now, super important in your notes. We have the same base, that's important, but it's single base. Up here, we had a base 2, a base 2, and another base 2. We had a bunch of them. To drop the power, which is what we want to do, you can only drop the power when you have a base 2 on one side and a base 2 on the other side. One base on each side. You couldn't drop it at this step. Look where I'm pointing. You can't drop the base on this step because you had 2 on this side and 1 on this side. So you had to combine these so you have one base on the left and one base on the right. So now you can say, okay, same. So 9x minus 7 equals 25x minus 35. And I have no clue what that is. Take away 9. 25, take away 9, what is that? 16x, I think it is. Yeah. Add 35, I get 28. So I get 28 over 16 equals x, which happens to reduce to 14 over, goes by 4s. 7 over 4 equals x. That's my solution. So the point of this example was for you to use your rules of exponents to first break everybody into base 2 or whatever you see, and then use more rules of exponents to combine multiple bases, okay, into a single base on one side and a single base on the other side. Only when you have single bases on each side can you drop the bases and work just with the powers. So you asked for it, Mitch. There you go.
I went ahead of you and I almost had it.
Okay, good. That's actually really good. I want to show you one more trick, if you will, because you're right. A lot of times I give you problems and then mom goes off the deep end. Okay. I had a joke there, but if I do it, I'll have every feminist in the world beating my head in. So I won't make that joke. All right. Can I erase this? Any
I'm
questions?
still copying the bottom part.
Okay,
The bottom
all right.
portion.
All right. while we're still copying, any questions on any of my steps? And not just what I did, but why I did them. That's what's super important.
Okay, you're good. Thank you.
Okay. Anybody else still copying? All right.
No.
Huh? No? All right. Last of these examples, and we'll move on to a new topic. What was the problem I wanted? Okay. 27 to the 5x minus 1 equals 1/9 to the 3 minus x. That would be good. Okay. What is the common base number? If you could look inside a 27 and look inside a 9, what can I reduce them all to? What base?
3.
3. Good. Excellent. 3. Now, the problem lies with that's a fraction. That's a 1/9. So I'm going to show you this in multiple steps. You can decide what you want to shortcut or not. So this is 3 to the third to the 5x minus 1 equals 1/3 to the second to the 3 minus x. Because 9 is 3 to the second. Hang on. This is easy, but for now, this is 3 to the 15x minus 3. We're kind of used to that. A power raised to a power, you multiply them together. But this is trickier. This is 3 to the negative 2 to the 3 minus x. This side over here requires an extra step because it's in the denominator. It's 1 over this. So we use our knowledge of negative powers to flip this up. Okay. Usually we go backwards. Usually we say 3 to the negative 2 is 1/3 squared. But now we're doing the same process. We're saying this can be turned into this, which means we have now this problem, 3 to the 15x minus 3 equals 3 to the negative 6 plus 2x. So right in here, somewhere in your notes, okay, you need to watch out because that 3 is in the denominator. And when you flip it up, it will introduce a negative power. Because you got to have a 3 and a 3, not a 1/3. The bases have to be identical, 3s and 3s. Come on. 13x equals negative 3. Did I miss the? Yeah, I did. So x is negative 3/13. Okay. From my notes, that's pretty much it. Chapter 10.2. Okay. We got one more thing in 10.2. Mom packs a lot in here, unfortunately. Chapter 10.2, we have exponential graphs, we have exponential equations. And those are examples of them. We have one more thing to cover in 10.2 before we do some fun stuff, before we get out of here. Not, I guess fun is a relative term, but so how are we doing on that example?
Would you be willing to do one more? Or like
Yeah.
at some point do another one? Like not, it doesn't need to be now, but like maybe tomorrow or something?
Oh, yeah.
Okay.
Well, one of the problems is, yeah, I can make tomorrow review. I think make one more of these right now.
I can just come in. I'll come in early tomorrow, and you can do one then. It's
Well,
just,
probably
my brain
everybody would probably want to see it. So
Okay.
I can do one for you early, and I would do one for the class also. Okay, so all right, I'm gonna erase unless somebody yells at me. Okay. Now the next thing we're going to learn in chapter 10.2 is exponential formulas. And I'm going to, I have to check Mom, but I will make sure I give you the formula. I don't expect you to memorize these. Okay. There's something called compound interest. That your bank or your credit union or whomever you do your banking with, they always use to calculate how much money they owe you or you owe them, for that matter. And aside, do not copy this down yet. In the bad old days, before computers, before fancy calculators, this is how they calculated interest. This great formula: principal times rate times time. Interest just means the extra money. I is short for interest. Maybe you do want to write this down. It just means the extra money. P means the principal. Okay, and that's the original money. Okay, R is the interest rate, but as a decimal, very important, which I'll show you in a second. And T is the time. Usually it's in terms of years. Now, this formula, I equals PRT, is what they use for hundreds and hundreds of years, because to calculate how much money you owe, you borrow money from the bank or from somebody, and they always say you pay it back with interest, meaning you pay back extra money. And this is the formula they use. The reason they use this is because they only did their calculations once a year. The math was too boggling for them. You only do this calculation once a year. So you don't get that extra money till the very end of the year or whatever yours was. Well, all of a sudden, with the advent of calculators, okay, they came up with another formula. A of T equals P times 1 plus, hang on, don't panic, R over N raised to the n times t. This is called the compound interest. And this allowed, calculators can do that. You buy an HP financial calculator for $1 billion, okay? And this formula is built into it. It's not that hard to use. We're going to work on it for a while. But this formula allows you to gain interest not once a year, but maybe 12 times a year, or maybe 52 times, or maybe twice a year, whatever. This formula is what calculators and computers use to make your calculation more often. More often, okay? Rather than once a year. So the A of t is the, mom calls it future value. Okay, it's the amount after time, amount after some time. Mom calls it FV, or future value, what you're going to have in the future. Okay, math, we would call it A of t, the amount after some time, A of t. P still stands for principal. Okay, which is still the original amount of money you put in. Okay, one is self-explanatory. Okay, R is the interest rate, always as a decimal, and 2 words, as decimal. Okay, now T is time. Notice that, okay, whatever, T is time, it's up here in exponential. And now this is the big thing, N. Okay, N is the number of times that we will calculate. God, I can't spell it. Calculate each year. Okay, so for example, if they said, I want to compound monthly, that means N is 12, because there are 12 months in a year. Okay, if they said weekly, then N is 52, because there's 52 weeks in a year. Okay, if they said daily, okay, then N is 365, because that's how many days there are in a year. So this formula works for all situations. If they said semi-annual, excuse me, that means 2. Okay, 2 times a year. Semi is half of something, so twice a year. Okay, so N is 2. So this one formula is useful in all kinds of circumstances. All kinds of circumstances, as long as you know what N stands for. Notice in this formula, N is used twice. N is used twice. You take the rate divided by N, and you take the power is N times time. So N is used twice in this formula. Okay, one last thing. We're going to do this on our calculators, and hopefully we'll all do it together. Okay. This is going to get rather ugly. Okay. Don't worry about it. Just let your calculator go. Just keep pushing the buttons and we'll do okay. It will get ugly. Keep in mind, we're also going to use PEMDAS. We're going to do inside the parentheses. But inside the parentheses, there's division. So we're going to do the division first. Then we're going to add 1. Then we're going to raise it all to that power. And then we're going to multiply by p, whatever that's going to be. So you have to do it in this order. First, we're going to do inside the parentheses. So we'll do r divided by n. Then we'll say plus 1. Then we'll raise it to this power, whatever that turns out to be. And then we'll take that answer and times it by p, because it's p times. Okay. Can I erase everything except the formula? I want to put a problem up on the board. Can I erase everything except the formula itself? Okay, here we go. Okay. Erase. Okay. Larry invests let's say $2,000 at 3.2% compounded monthly. Okay. Larry invests $2,000 at 3.2%, which is a good rate if you can find it anywhere, compounded monthly. How much will he have in 6 years? Larry invests $2,000 at 3.2% compounded monthly. How much will he have in 6 years? Okay. So let's list some things. What is my principal? What am I starting with originally?
2,000.
2,000. Okay. What is my interest rate? What is my R value?
3.2.
Okay. It is 3.2%, but it has to be 0.032. Very, very important. Because if you go back and look at the notes, every time I talked about the interest rate, okay, I said as a decimal. So you have 3.2%, you got to divide it by 100 or slide the decimal point back 2 places to get 0 or 0.032. Remember how you convert percents to decimals and decimals back and forth? Well, you got to do that now. What is my N value? What is my N value? How many times will I do this conversion? Or this calculation, I should say.
Maybe
Uh,
12.
Equals 12.
I do it, N is 12. And what is my T value? For how long? 6. So these are really important things that you have to identify. The principal was 2,000. Okay. The rate written as a decimal is 0.032. The N is 12 because it was monthly. Okay, it said that in the problem, monthly. And time is 6 because we're going for 6 years. So here we go. Mom, or when you write this, they'll say the future value. What is the value? How much will we have in the future? That equals 2,000 times 1 plus 0.032 over 12 raised to the 12 times 6 power. Okay, at this point, we're on our calculators. And each of you can do things differently on your calculator, but I'm going to do what I said. Okay, and I'm going to start inside. So I'm going to go 0.032, whatever that is, divided by 12. Okay, now I got some really big, ugly decimal number, 0.00266666666, whatever. Okay, I don't care. I don't care. Add 1 to it, plus 1. Okay. And again, I don't care what that is. I'm going to write it down here so that you can be double checking, but you should have 1.0026666, and that'll be 72. 12 times 6 is 72. Don't worry that your calculator, if you guys don't have this TI-36, your calculator does some weird stuff. Just don't worry about it. Don't panic. Okay. Just write this down. Now we're going to take this and we're going to raise it, okay, to the 72 power. On my TI, whatever, I have that button. I have that button. On a standard scientific calculator, you might have that button, that up caret again. That's almost universal for exponents. So I'm going to take this, I'm going to use this calculator. I'm going to raise it to answer raised to the 72 power. Okay. And now I have 2,000 times 1.21136, blah, 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 blah. Okay. And so I times it by 2,000. And I get 2422.7218. And since this is money, okay, and you have to read directions, at the most it would be 2422.72 because money goes to dollars and cents. Unless they say something else, unless mom or my instructions say rounded nearest dollar, that would be $23. But I'm not worried about minor details now. I'm worried about my math. Okay. And again, once you write this formula down, hang on one second, Mitch. Once you write this down, then you don't even have to show me all these other steps. They could all be done on your calculator. Once you show me the input, everything else is done on your calculator. You don't have to show me any of these steps, okay? Because they're all on your calculator. Mitch, you had a question.
Sorry, I'm a million questions tonight.
Okay. Nope,
So
no problems.
I put that whole thing in the calculator all at once instead of doing it step by step, and I got the same answer. Is that just a coincidence, or is that
no? On this calculator, the 36X, okay, actually has some intelligence to it, and so it will understand what you're doing. A different scientific calculator might not. Okay, so I show you all these steps in case you're using a different calculator. Okay, but if your calculator will do it all at once, good for you. Go for it. That's why I said Once you show me this, everything can be done on your calculator and I don't care anymore. Is that okay?
Yeah.
Okay. And you said, you've been asking a million. Do you have a million more? You can keep asking
No.
because I love questions. Huh? I'm serious. I love questions. No? How about anybody
It's
else?
really straightforward. It's pretty good.
Okay. What about anybody else? Did you have any trouble with your calculators one way or the other? Whichever calculator do you have? You guys okay with this? Okay, let's try one more. Then we'll move on to a new topic, or slightly new topic. So Mitch
Yes.
invests his whole life savings of $500 at 1.75% compounded weekly for 10 years. How much does he have? How much is Mitch worth in 10 years? Okay, so go for it. Oops. So we would say the future value is 500 times 1 plus 0.0175 over 52 raised to the 52 times 10 power. So that would be that would be plugging these numbers into that formula. And remember, I will give you that formula. Okay, I will give it to you. You need to know what each of those letters means and how to apply them, but I will give you the formula. You do not have to memorize it. All right, so let's see, what do I have? Turn it on. I get $595.60 or 61 cents or something like that.
Yes.
Okay. So equals 595.6055, which is 595 point, let's say $61.
Not worth it.
Yeah, I agree. Mitch is not, I mean, I'm sorry. Yeah, in the bad old days, you caught it, okay. In the bad old days, okay, you used to be able to get 6 to 13% if you put things in the bank or in the credit union, or if you invested things in a money market back in the 70s and the 80s and whatever. You used to be able to get that. That was worth it. That was worth it. Now you put something in the bank and you get a CD at maybe 1.7%. It's almost not worth it. It really isn't. So, and I agree. So that's called compound interest. Okay. Now, we're going to go to another formula. And again, I'll give you this other formula, but it's slightly different. This compound interest is a good formula when we're using what's called discrete jumps, when n is 12 once every month, when n is 52 once a week. Okay, when we have this. But what if we have something called continuous growth? Continuous growth. That means something is changing or growing instantly by the second. Okay, that's known as continuous growth. And it's instant change. That's what it means. And it is used a lot, not only, but it's used a lot when you're studying living things, when you're studying plants that are growing, bacteria that's multiplying, people that are multiplying, growing, having babies, all that stuff. Okay? Because people don't have babies once a week. Okay, they do them randomly all around the world. Plants don't grow, 1 week they're not here, or 1 week they're 1 inch, and then the next week they're 5 inches, and the next week they're 15, or whatever they do. Plants grow continually, whatever. So we have something called continuous growth. And the formula for that is A of t equals P times E raised to the R times T. Okay, I'll show you this. Again, A of T stands for the future value, the growth. Okay, P is still the principal. That's not going to change. P is the principal. R is the rate as a decimal. T is the time. The only thing different here is this number E. Okay, E is a very special number in math. Okay, it's named after a guy who actually found a way to calculate it. Okay, his name is, in his own country, his name is Euler, but it's pronounced, we as Americans, because everybody has to speak like us, we would say that's Euler. Okay, but actually it's Euler, but his name starts with an E. So math world and science world decided to honor him for figuring out how to calculate this number, and so they called this number E. Now it's on your calculator. Okay, where'd it go on my calculator? Oh, turn it on. Oh, wait a minute, where'd it go on my calculator? It disappeared. Clear.
At 5?
What?
Oh, no.
Wait, it was just there. What?
Above table?
Where's table?
Next
No,
to
that's
clear.
express. That says expression. No, come on.
Is it not 4 down on under second, the fourth button under second? With pi?
Oh, yes. I was using it all afternoon to practice that. Yes. You got a button that has pi E I. Okay. So pi EI. So if we want that clear, sorry, if you hit that button twice, okay, you'll see a little E on your calculator. If you press FD, the FD key, and then enter, okay, you'll see that it's 2.71828. And you know what? I don't care. I care that you can get it on your calculator. Now, some of your calculators, you may see an LN button, depending on your scientific calculator, and above it, you might see this, e to the x. That's how you're going to activate it on your other calculator. But on this scientific calculator, that's how you get it. There's a button right above, well, right above the power or whatever, fourth one down, you said. Okay, but you push it twice, and that tells you the decimal equivalent. That's the thing that Euler figured out how to calculate with a lot of accuracy. But nowadays, we don't have to do the calculation. Okay, our calculator will do it for us, either our TI-36 or somebody else's calculator might have an LN button with that above it. Okay,
Is the button right above it the same E as well? There's like a E exponent and then like a 10 exponent.
what calculator are you using?
The TI-36X Pro.
What button right above where? I don't see it.
The button above the pi
Oh,
button.
yes, the button right above it. That will also do it. That will do it also. Thank you. Right above it, you're right. You have an E to the blank and 10 to the blank. That button will also do it. Okay. In fact, that one's probably going to be easier. So let's talk about you have 5,000 bacteria growing at a rate of, I don't know, let's say 7.2%, okay, per whatever, per hour. And I want to know how many per hour. And I want to know how many will I have after 18 hours. So same idea. I'm starting with 5,000 little bacteria. They grow at 7% per hour. Those little buggers just grow and grow and grow. Okay. And how much will I have after 18 hours? So this would be the future value, the total number of bacteria I'll have is going to be 5,000 times E raised to the 0.072 times 18. Your calculator will do that. If you push this E to the blank button up there, okay? If you push the E to the blank button and you go 0.072 times 18, okay, you don't have to do that math at all. If you just do that by pressing this E to the box button and then putting that in the box, 0.072 times 18, okay, your calculator will do it. And I get 3 point something. And then if I multiply it by 5,000, okay, I'm going to have 18,272.73, I'm sorry, 0.24398. Okay, were you guys able to get your calculator to do that?
Yes.
Yeah, okay. Now, here's a little catch. Money we can have dollars and cents. Okay. But people, bacteria, living objects, you can't have a piece of a bacteria. So typically for living things, and this is where you have to have some understanding of the meaning of the words, the English meaning. We would round this automatically down to 18,273 bacteria. One of them is about ready to split or is going to split, or one of them's pregnant or something, I don't know. But for living objects, you can't have a partial living object. So we always round them to whole things, and we always round them down. Okay. So let's try something different. Same formula. Let's say the population, people in a certain town. Let's say we have 120,000 people in a small town somewhere, and they're growing at a rate of, let's say 4.12% per year. How many people will be there in 7 years? So I get 160,114.9097, but based upon what I just said, we'd have 160,114 people, and one of those is very, very, very pregnant. Is that okay? That all right for everybody? In section 10.2, Mom will throw a couple formulas or a couple word problems at you that will either use this formula or this formula. Okay. Now, Mom may not give you the actual formula within her problem, but when I give it on a test or when I give it on a quiz, I will give this formula to you. Okay. You won't have to worry about memorizing. You will have to know, again, what do each of the letters stand for and how do I input it? We doing okay?
Yes.
All right. Then I want to erase and go off to a last topic. And we're not going to get all the way through it tonight. I am watching the time a little bit, but this will all be done on our calculators with a little bit of background. So I'd like to erase the board and start a new thing, a little bit of section 10.3. Are we okay? All right. I don't hear anybody yelling still. And Mitch must be eating again because he's not asking questions.
How do you know I ate before?
I can see you. You got a camera on. What do you mean? How do I know? Okay. Well, Jeez. Okay. In chapter 10.3, we're going to start by introducing what's called a logarithm. Okay. And nobody knows how to spell it, so we always abbreviate it LOG. Okay. Mathematicians can't remember how to spell it. Nobody can spell it. Okay. So it's always called a log. Now, I want to give you some background. Do you guys remember in grade school, you had that grayish paper with blue lines on it? I don't know if you guys remember that. And you tried to write on it, and then you tried to erase it because you made a mistake and the paper ripped and you got all frustrated and pissed off and everything like that. Anybody? Does that bring back any memories to anybody?
Me? Yeah.
I hated that. I mean, that, you know, I was ready to quit right there. Well, pretend that this is what it is. When we write a logarithm, okay, L-O-G, okay, log, like that. We have something called a base. Now, the base is written down here, like 5. That's called the base. Okay, and then of 7, and it equals X. So when you write this, you need to be careful how you write this and how you say this. Okay, the base, you know how an exponent is like written up here a little bit higher than the normal number? Well, the logarithm base is written down here. If you're careless and write it there, like right in the middle or something like that, you're going to confuse the heck out of everybody. That's wrong. So when we say base, it's called a subscripted variable. It's written a little bit lower than the rest of the word. Okay, so be careful as you write that. Now, how do we say this? And this isn't Foster, well, it is me being nitpicky and kind of anal about all this stuff. But actually, if you go look it up in books, this is the correct way. You either say the log, comma, base 5 of 7. You can either say is or equals X, or you say the log of 7, comma, base 5. And again, is either is or equals X. That doesn't matter. Is X equals X. The point I'm trying to make 2 points here. First off, logarithm is actually a function. It's like f of X. Okay, it's a function that we plug into, that your calculator has built into it. So when we're saying log of 7, okay, the of is a clue to everybody that this is a function. It's called the logarithmic function, log of 7. We must say base 5. There's a reason for that, but I'll worry about it a little bit later. Okay, we must say whatever the base is. Log base 5 of 7, or log of 7 base 5, one way or another. Now I'm going to continually correct you because I want you to be able to go forward not sounding like a bozo. Okay, it's log of 5 base 7 or log of 7 base 5. That's how you say it. Okay, and that's how you write it. The base 5 or whatever the base is. It doesn't have to be 5. It could be 3, it could be 9, it could be anything. Okay, but the base is always a subscripted variable. It's written a little bit lower than the rest of the problem. Now, I remember one year, apparently I made a great impact on a person. She kept writing this. Okay. And I kept trying to get her to change. No. The 5 isn't way down here. It's just a little bit down. Okay. And the 7 is on the same line as the log of 7, base 5, like that. That's how you write it. Log of 7, base 5. So anyway, I'll continue to push that and correct that. Okay, as we use more and more logarithms. What I want to do tonight is make sure you guys can use your calculator properly. That's all I want to do tonight. I'm not going to do any more than introduce how you write a log, how you say a log, and how you use it on your calculator. I won't try to explain what the heck it means yet. Okay, but let's go to log base 5 of 7 and just see, can we do that on our calculator? Now, there's 2 ways to do this on your calculator. And I'd like you to try both ways if you can. On the 36X, you have an ln and a log button. Press that. Clear. Keep pressing it until you get this. Okay. Press the ln log button, whatever that is. Okay. Until you see this. Okay. So what you're doing is that one button cycles through a bunch of possible menus, and you just stop at the one you want. So go ahead, and once you have that on your menu, then input a 5 for that. Use your arrow to input a 7 for that, and then press enter and see what we get. And I get 1.20906 something or other. Are you guys getting that?
Yeah.
Okay, cool. Now, is there anybody who does not have this feature on your calculator? You may have it in a different menu.
I don't.
You don't? Okay, cool. That's okay. Because there's something called, well, I'm just going to show it to you. If you turn this into log of 7 over log of 5, if you take this problem here, log base 5 of 7, and you turn it into log of 7 divided by log of 5. Well, how do you do that on your calculator? Well, you hit the log button of 7. Okay. And then you hit the divided button, log of 5. And then you hit the enter key. Okay. Who said they don't?
Me, Natalie.
Natalie. Okay. What calculator are you using? What type? What number?
It's the TI 30X8.
Okay. Well, all right. This should work then. Then you enter log of 7. So you still have a log button, don't you, on your calculator, LOG?
Yes, but every time I push it, it just goes to error.
Okay. So you have to enter 7 log. Try that. Okay.
Okay, I got some decimals.
Okay. Divided by, okay, and now to get this calculator to do it right, you've got to go parentheses 5 log. You got to use that parenthesis. So 7 log divided by 5 log. And then press enter or equals or whatever you do on your calculator. And you should get the same answer. Do you?
No, I'm not. I'm getting like a 0.6 number instead of a 1.2.
Okay. Okay. That 0.6 is just for that answer. Okay. So here we go. Let's try it again. Push 7 log and then say enter. 7 log and then equals. Okay.
I think I got it. I have to press equals twice.
Okay, yeah, because 1 equals tells you what that answer is. The second equal tells you what the whole answer is.
Yes.
Okay, so you got it now?
Yes, thank you.
Okay, so, but wait a minute. I want everybody on their calculator to try not using your fancy button, but can you do this on your calculator? So the log base 5 of 7 can be taken apart as log of 7 over log of 5. And then you do those as a separate calculation. Try that. Make sure you can get the same answer. Okay. Anybody having trouble using log of 7 divided by log of 5? And like Natalie was saying, sometimes we have to trick our calculators. The way your calculator is built, its logic keys force us to enter things backwards than we normally do. But once you figure out your calculator, it's fine. Okay, it doesn't matter. So can everybody find log base 5 of 7 using 2 different ways, assuming you have this button? Okay, Natalie, if you look around, you might have it hidden on your calculator somewhere. It's no big deal if you don't, because this wasn't all that bad. Okay, so I want to see, can everybody find log base 3.1 of 15.2? Log base 3.1 of 15.2. Sure wish mine wouldn't turn off so damn fast.
Wait, sorry, that was 3.1?
3.1, log base 3.1 of 15.2. Whatever, we'll worry about rounding later, but 2.405. Try using the other way also. You will find that there's a time when the other way, that is log of 15.2, all divided by log of 3.1. There's a time when that will be more convenient for us than this magic button. So make sure you can kind of do it both ways. It doesn't matter. And I got the same answer whichever way I did it, but you guys doing it?
Yeah.
Okay. So if I gave you a whole worksheet of these, log, base, somebody of somebody else, could you use your calculator to work them out? That's the question I need to ask.
Yes.
Everybody
Yes.
pretty comfortable? Yeah, okay, cool.
Yeah.
Now, it turns out that there are two special logarithms. Two special logarithms. Okay. The first one is called the common log. And when we write log of 5, for example, what's missing when I write log of 5?
The base.
The base, okay? So the base is missing, and it is always assumed, if it's missing, it's assumed to be base 10. That's called the common log. Hang on. Okay. So when you press your log buttons and you just find the word log, okay, and parentheses like that, it's automatically calculating as if it were base 10. Okay, so the word log with no base implies always base 10. That's why it's important when I was making that big deal about log base 5 of 7 and all that crud. That's an entirely different answer than log of 7. Changing the base changes everything about the problem. So that's why it's important to stress the base was 5 here, the base is 10 here. And when we leave the base off, it's assumed to be a 10. So what's the log of 5, anybody? I get 699 or 6989. You guys get that?
0.6, yes.
0.6989.
69897 something. Okay, that's called the common log. Okay. There is another log known as the natural log. Okay, and that's the ln. Okay, ln. Okay, I like to think of it as the Spanish log, ln. Get it? Some people, okay, bad joke. Some people, there's, yeah, thank you. Okay, there's confusion in the world about how to pronounce that. Okay, some people call it ln, just exactly what you see. Some people call it lawn, L-A-W-N, lawn, as in the green stuff out in your front yard or your backyard. Okay, and some people don't know what to call it, so they just say the natural log. Okay, there's all kinds of confusion in the world. Now, don't get me wrong, that confusion about how to say it doesn't mean it's not important. It's incredibly important. Incredibly important. Okay, it works for all natural sciences. It's really good in the natural sciences. It's excellent in statistics. You'll be using this quite a bit in the future classes. Okay, you'll be using the log also in future classes, but this natural log, just because we don't know how to say it, we're not in agreement about how to say it, doesn't mean it's not important. It's very important. So I like to say ln. Okay, I know some people write lawn, okay, and other people just call it the natural log. You can call it anything you want, one of those, I don't care. So the ln of 5, again, if you push that magic button on your calculator, or Natalie, I think you have to go 5 ln. You have to say it backwards, the number and then the function ln, but it still works. Okay. Clear ln5. 1.609, something or other. 609.437, something. You guys all get that?
C.
Okay. C. I get it. LN, C. Dos Equis, tres Equis. Modelo. Yum. So what I wanted to introduce tonight, what did I learn in high school Spanish? ¿Dónde está la biblioteca? ¿Dónde está el baño? And yo quiero tres cervezas, por favor. That was it. That was my high school Spanish. Thank you. Okay. So in 10.3, we introduced, all right, so how many people have I offended with that one? I don't know. The concept of logarithms, how to write them. Okay. We've introduced how to calculate logarithms of different bases in two different ways. Okay. And I've introduced something called the common log, which is implied to be base 10. When we don't write it, it's base 10. Like, when we do the square root of 7, the index is implied to be an automatic 2. Okay. Same thing with the common log. The base is implied to be an automatic 10, and your calculator knows that. Okay. And then we introduce something called the natural log, which has 3 or 4 different ways of saying it, but notice it comes up with a different answer. And why they're different, I'll explain at a future date. So with that, I'm done. I will stop recording now. And if you want to stick around and do you want me to do another one of those common base